Good morning, this again is Dr. Jingbo Louise Liu. Today we are going to continue your chapter 5. Particularly, we are going to be more focusing on the preparation of alkene. So totally we are going to discuss 4 different types of alkene preparation methods through the beta elimination reaction. The following is a very brief summary. The first method we can use is called dehydrogenation of your alkane to remove a hydrogen molecule and then produce an alkene. This reaction normally occurs at a very high temperature. It's an industry process. Normally you can use a noble metal as a catalyst. The second method is called dehydration of an alcohol to remove a water molecule and produce your alkene. This reaction requires a strong acid such as sulfuric acid as your homogeneous catalyst. Another method is called dehydrogenation of an hydrogen halides from your alcohol halides to produce your alkene. This reaction is also a beta elimination reaction, and a strong base such as sodium alkoxide usually is required. Another method is called dehydrogenation of an dihaloalkane. So usually you have an alcohol halides. This is dihalides. You can use alcoholic potassium hydroxide as a catalyst to convert the alcohol dihalides into alkene through elimination reaction. So further on, we are going to discuss each different types of reaction. First one is called the dehydrogenation reaction. If you have a molecule, for example, you have 2 carbons, 1 carbon connected to X and 1 carbon connected to Y. The carbon connected to X, let me call it alpha carbon. This carbon called the beta carbon. If you remove XY, so this reaction you call the beta elimination. So from this compound, so you have XY as your substituents. You remove the X and Y to produce the carbon double bond. This reaction, this process is called beta elimination. The elimination of 2 substituents from the adjacent carbons, alpha and beta carbon, is going to result in the formation of alkene. So for example, if you have ethane at 750 Celsius, a hydrogen molecule will be removed from 2 carbons, and then you produce an ethane. Similarly, if you have propane under very high temperature, 700 Celsius, you remove 1 mole of a hydrogen molecule, so you produce propane. So in this case, if your X and Y, they both the same as hydrogen, so you have X and Y, they both hydrogens. This reaction is called dehydrogenation. This reaction, as we mentioned, is a high temperature industry process. I believe the metal catalyst will help you to improve the reaction rate and also decrease the activation energy. Another method is called dehydration of alcohols. If you have your, say, alpha carbon, you have OH substituents. This beta carbon, you have hydrogen. You remove a water molecule from the alpha and the beta carbon, you are going to produce an hexene. For example, I have a cyclohexanol. So you remove your OH from your alpha carbon, hydrogen from your beta carbon, you produce a cyclohexene. So this reaction requires a strong acid such as sulfuric acid. Reaction occurs at 140 Celsius. It's a very effective reaction. Production yield 79 to approximately 87%. If I have another molecule which is tertiary alcohol, So I have my 2-methyl 2-propanol. You are going to heat it up, adding sulfuric acid as your catalyst. This reaction will result in the 2-methylpropene. So this one I may have a question for everybody. So which one is considered alpha carbon? I will consider the carbon connected to OH as your alpha carbon. This carbon in the methyl group, all the carbons you call the beta carbon. These 3 beta carbons, they are identical. So meaning you remove a hydrogen from each of the carbon, they are essentially the same. If you have your X is the same as your OH hydroxyl group, your Y is hydrogen. In this case, this process is called dehydration. Again, catalyzing by a strong acid, such as your sulfuric acid. If you have ethanol, you produce isolene by removing a water. So another important point is about the hydration or dehydration, hydrogenation, dehalogenation, etc., etc. All of these different reactions, they are related to regioselectivity. What do you mean by regioselectivity? Selectivity meaning one product is favorable compared with the others. So one product is preferentially formed. You call it selectivity. Regioselective reaction refers to the process preferentially in one direction, preferred in one direction, such as if you have this molecule, let's see, we have 1, 2, 3, 4, 2, you have number 2 methyl, 2 butanol. Let's count the carbon. So this carbon number 2, I consider this my alpha carbon. So you have this alpha carbon. There's alpha carbon. Here is 1 carbon. You can call it beta carbon. This number 3 carbon, you can call it beta. This number 1 beta. This number 1 and this carbon, this methyl carbon, they are identical. Number 3 carbon, they're different from the others. So therefore, you have 2 different carbons. So in your 2-methyl 2-butanol, you are going to have 2 different carbons. So this carbon over here and this number 1 carbon, they are the methyl carbon, primary carbon. This number 3, you call the secondary carbon. Secondary carbon, as we studied before, so it's going to result in the mole substituted alkene. So if the carbon from number 3 going to be removed, the hydrogen bonded with carbon 3, this beta carbon, so which is secondary. The secondary hydrogen and OH going to be removed, so you form 2-methyl 2-butane. This molecule has more substituents. Therefore, this molecule is more favorable. If this carbon 1 hydrogen, your primary hydrogen, and your OH going to be removed, so you form 1,2 double bond. This case, you have 2-methyl 1-butane. This 1-butane is less favorable. In this case, the product, this reaction produced the product, so 2-butane with more substituted alkene, this is more stable. This selectivity you call the regioselectivity. So that dehydration of 2-methyl 2-butyl is regioselective, forming the more substituted alkene. And which rule you are going to use? When we discussing the selectivity, we are going to use Ch5 rule. This rule, also called Ch5 rule. Ch5 rule states the alkene formed in the greatest amount is that one which corresponding to the removal of your hydrogen from the beta carbon having the fewest hydrogens. Or let me restate it. The Ch5's rule states the greater amount of alkene will be formed by removing hydrogen from the beta carbon with smaller amount of hydrogens. The less hydrogen you have, the easier going to be removed. So the alternatively, this beta elimination of alcohol is going to yield the most highly substituted alkene. This highly substituted alkene will be your major product. So if you have different beta carbons, for example, you have this molecule, just general speaking, you have your alpha carbon, which is connected to your OH hydroxyl group. You have beta carbon 1, have 2 hydrogens. You have beta carbon 2, let me call it beta carbon, have 3 hydrogens. You have beta carbon 3, you have 1 hydrogen. Which one will be involved in reaction? So the one with the fewer hydrogen, this beta carbon 3 will be involved in the reaction. Therefore, the double bond will be formed with your alpha with beta 3. So you form 1 substituent, 2 substituents, 3 and 4. You form 4 substituted alkene. The more the substituents you have, the more product yield this one will be. So that's about your selectivity. So your selectivity also have a stereoisomer preference. In this case, a stereoselective reaction yields the isomer in preference over another one. One isomer is in preference. So which isomer is more stable? Usually the stereoisomer with the 2 groups, similar groups located in the opposite position, to eliminate the van der Waals strain, to mitigate the steric strain, steric hindrance. If I have this dehydration reaction, so I have my 3 pentanol, I have 1, 2, 3, 4, 5, 3 pentanol. So you are going to have, let me see, you have both carbon, both beta carbon, they are identical. You can form a trans and cis isomers, right? You have two isomers. Which isomer will be more predominating? So the trans will be your major product, which turns out to be 75%. So this is about the elimination of hydration of your alcohol through the dehydration reaction. The dehydration reaction, including the other one, they may follow 2 different mechanisms. One is called E1, another mechanism is called E2. The mechanism again is a processing for us to describe the step-by-step formation of a product based on the chemical reaction. In this case, you see this alcohol under the heat, under the sulfuric acid as a catalyst to produce a propane and water. So you write it down your acid above this reaction arrow, representing the acid is a catalyst. So this reaction is a catalytic reaction. Also, you require temperature increase. You need to heat it up. So this reaction again, so you have terbutyl alcohol. So your carbon connected to the 3 different methyl groups, 3 beta carbon, they're all the same. What's going to happen during the elimination reaction? This reaction, let me say this is an E1 mechanism. You are going to involve 3 different steps. The first one called protonation, the second one called dissociation. Does this sound familiar for you? It sounds like SN1 reaction, right? Protonation, dissociation. After the dissociation, you are not going to have a substitution reaction. You are going to have elimination reaction. The third step called deprotonation. What does that mean? Let's take a look at this tributyl alcohol. So again, you have your alpha carbon, you have 3 beta carbons, and then you have your alcohol. In your solution, you also have your hydronium. Very strong acid, sulfuric acid is going to provide hydronium. This hydronium has a positively charged hydrogen. So your lone paired oxygen is going to attract it to the hydrogen to form another thing called oxonium. In this case, it's a terbutyloxonium cation. Because your hydronium loses a hydrogen plus, so this reaction, this hydrogen-oxygen bond cleavage is heterolytic. 2 electrons go to oxygen. Therefore, your oxygen is going to retain 2 lone pairs, become a water molecule. This first step, you call it protonation. This protonation is an acid-base reaction actually. Your alcohol is protonated by the strong base which created a hydronium. The hydronium which is generated from your strong acid, so it's going to react with your alcohol. The sulfuric acid again dissolved in water and then forms hydronium ions. This is your first step. Second step, as we mentioned before, this oxonium cation is not stable, it's an intermediate. This ion is going to be dissociated into a carbocation. If you have your tertiary carbon, particularly this tertiary carbocation is more stable compared with secondary and primary and methyl carbocation. In this case, you form a tertiary carbocation and water. Again, you remove another water molecule. The carbon-oxygen bond is going to subject to the heterolytic bond cleavage. So carbon becomes positive charge. Oxygen gains 2 more electrons, retains 2 more electrons, becomes water molecule. This reaction is considered the carbon-oxygen bond breaks to form a water molecule which is more stable and also form a fairly stable or relatively stable tertiary carbocation like this one. So terbutyl carbocation. So this second step, again, as we mentioned before, this is your slow step, is your rate determining step. This step only involved in 1 molecule, you call the unimolecular reaction. Therefore, this reaction is called E1. Because the reaction is the elimination reaction, you call it E reaction. Where the elimination is going to happen, what's going to be eliminated? So you have this carbocation. In these 3 different carbons, you also have a hydrogen-carbon bond. What's going to happen? In your solution, you have lots of waters. Your water oxygen has a lone pair. Oxygen has lone pair. This oxygen attracted to the hydrogen. Your hydrogen-carbon bond will be break up. Hydrogen-carbon bond break up. This hydrogen lose the electrons as a positively charged ion going to be attracted by water, by the oxygen end of water. And then this carbon-hydrogen bond break up. Carbon take away 2 electrons, so neutralize it. Therefore, you form a carbon-carbon double bond. That's how your 2-methylpropene is going to be produced, and then you produce your hydronium. This third step reaction, actually in this third step, your water technically acting as a base. This base attracted to the proton to form a hydronium. Therefore, the acid is used, actually this reforms your acid catalyst, and then you produce a highly substituted propane. This reaction is called E1. E1 reaction involved in 3 steps: protonation, dissociation, deprotonation. Deprotonation is equivalent to the elimination. So your second step, dissociation, is a slow step, which only involves in a unimolecular reaction. Therefore, you call this reaction E1 reaction. E1 reaction is also a first order elimination reaction. E1 reaction is more applicable for the tertiary alcohol. If you have the other types of alcohol, you may go through E2 elimination, such as if you have halogens, so you have your alcohol halides. The alcohol halides, particularly you have primary ones, you may go through E2 reaction. So again, dehydrohalogenation, meaning you remove the HCl or HX, hydrogen halides. So this is a loss of hydrogen and halogen to form from your alcohol halides to form alkene. This reaction is also considered beta elimination. Dehydrohalogenation is also a beta elimination. In this case, due to this HCl or hydrogen halides formation, you may need a strong base to neutralize it. General reaction of this dehydrohalogenation will be two carbons connected to halides connected to hydrogen, and then under this sodium ethoxide, this alkoxide, this is ethoxide, hydrogen and halides going to be removed. Alpha carbon, beta carbon, your beta carbon, beta halides will be removed. You produce NaCl and alcohol. That's what happened. This chemical reaction has a reaction rate. The reaction rate depends on the concentration of your base and the alcohol halides. So therefore, the reaction is considered E2 reaction. For example, if I have this one chloro actually is octadecane. So you have a totally 20 different carbons. So what's going to happen? You use potassium alkoxide under the MSO as a solvent, room temperature. The reaction will produce the octane. 1-octadecane. So this is your compounds which produced. So alcohol in this case is your solvent, and then you also need a strong base. So strong base is more like a neutralize your HCl which formed. And then this dehydrohalogenation also follows Ch5's rule. Also meaning the more substituted compounds, the higher the yield product is. For example, if I have 2 isobutane, so you are going to remove the beta hydrogen carbon from beta carbon. You have, this is my alpha carbon, beta carbon 1, beta carbon 2, they are the same, got beta carbon 3. So if you remove the Br from carbon 2 and the Br from carbon hydrogen from carbon 3, you are going to produce this 2-methyl-2-butane. You have 3 substituents. This molecule is more variable. So again, the beta carbon with fewer hydrogens will be involved in reaction. That's your Ch5's rule showed you. So this is the same as your dehydration reaction. So the reaction for this dehydrohalogenation is also going to produce the stereoselective isomer. Normally your trans isomer is preferable. The selectively preferentially forming the most stable trans stereoisomer, such as I have this molecule. So this carbon, you have a 2 beta carbons. Both they are identical. If you form a cis isomer and a trans isomer helps you to eliminate the van der Waals strain, meaning the steric hindrance will be mitigated, will be decreased. Therefore, you form a trans isomer. For most of the alkene. However, when you form this cycloalkene, we need to pay attention. So dehydrohalogenation of your cycloalkyl halides also produce alkene. In this case, you produce a cycloalkene. For example, I have cyclohexyl chlorides. This chloride and one of the beta carbon will be removed. You form a cyclohexene. This reaction occurs in a very strong base like sodium isoxide in the alcohol ethanol and 55 Celsius. It's a very good reaction, produce 100% cyclohexene. If you have a larger molecule, I have my bromo cyclodecane. You have 10 different carbons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 different carbons. Also, you use a potassium alkoxide in the ethanol. What's going to happen? You form two different types of formulas. So this molecule, this part, this is a cis formula. This one is a trans. Actually, this cis, this molecule is more dominating. So you produce a molecule due to the torsional strain, angle strain. You want to eliminate the angle strain in this case. Again, when you form the cyclo compounds, be a little bit careful. Do you have cis more stable or trans? Depends. If you have cyclohexane, they are less than 10 carbons. So you may have that which cis is more dominating. Again, larger ring may give the cis-trans mixture. So in this case, you have this ring is still considered reasonably smaller one, but be careful. This case, cis is most stable. The reason is you want to eliminate the torsional strain or angle strains. Regarding this E2 elimination reaction, so you remove hydrogen halides from your alcohol halides. So you may ask yourself, you have 4 different halides. I have fluoro, chloro, bromo, iodo. Which one is the best leaving group? All of these halides, you call them leaving group. Which one do you think is the better leaving group? Fluoro, chloro, bromo, iodo? What you are going to think? You are going to think about electronegativity. So your fluorine, this fluorine has larger electronegativity, meaning bonded with a carbon more solidly. Therefore, fluorine is the worst leaving group. The chemical reaction rate will be the slowest one. And then your iodo, carbon iodo bond is the weakest bond. So therefore, iodine is the best leaving group. So the reaction rate for the halides will be increasing from fluoro, chloro, bromo to iodo. Again, fluoro is the worst leaving group. Chloro is second worst. Bromine is better. Iodo is the best one. Ci has the weakest bond strength. Therefore, iodine, that iodo will be the best leaving group. So we are going to see these different reactions. When you have this dehydrohalogenation, couple minutes ago we mentioned the E2 reaction. So this dehydrohalogenation, so you can subject to the transition state. Imagine this way. So this carbon, so you are going to remove the Br and one of the hydrogen. So you form this kind of compounds. This is what we are going to see. And these 2 different compounds, they are going to be formed, and then you are going to generate some hindrance. This second hindrance, this second transition state is more stable because you have more substituents. The more substituents you have, the more stable product you are going to be involved in. So if you have lower activation energy, that direction is going to be more favorable. So you have these different highlights. This do a little comparison. You have isobromide, you have isopropylbromide, you have a 2-bromo, 2-methyl butane. So the reaction rate, the most substituted one, will have the highest relative reaction rate. This is about your elimination reaction. Your elimination reaction also related to the different isomers. If I have these larger molecules, I have the cis-4-terbutyl cyclohexobromide, and you have trans, you have 2 molecules. If you produce the cyclohexene, you figure out you have the same product. You have the same product. What's happening in this case? What happened? You have this terbutyl, so they both in the equatorial position. So this cis bromo is in axial position. This bromo in equatorial position. So this cis reactant is more reactive. So the cis isomer reacts much faster compared with trans. The reason is this axial Br is subject to the higher van der Waals strain compared with your carbon 3 and carbon 5 hydrogen. So the bromo is going to be more readily to be removed. So that's some of the chemical reactions. And also I provide another several different elimination reactions, writing down in the different conformation. You have Newman projections. These 3 examples will be your take-home message. Produce different products. Ask yourself which one is more favorable one. Again, cis less than trans. So more substituted, more than the less substituted. So trans is the most dominating and based on trans and followed by cis and followed by less substituted one. And about the leaving group, as we mentioned, the leaving group related to highlights. The highlights, so which with the lower electronegativity, such as aldo, that's the one which is the best leaving group. The choice of your halogens is going to affect on the reaction rate and reaction constant in order to produce alkene. The reaction rate, the rate is going to be increasing from fluoro to chloro to bromo and all the way to aldo. Again, your fluoride is not a very good leaving group, meaning the reaction rate will be correspondingly slower. There is another point we didn't mention before. So for your hydrogens, you can have different isomers. So you can have different isotopes. Therefore, we need to consider isotopic effects, such as if you have carbon-hydrogen bond, one of the hydrogen replaced by deuterium, so you form hydrogen-deuterium bond, CD bond, carbon-deuterium bond. This bond has approximately 12 kilojoules per mole bond energy compared with hydrogen-carbon bond. Therefore, the reaction rate constant for the elementary step, so where you break the carbon deuterium bond, so that rate constant will be smaller than the hydrogen-carbon bond, because the hydrogen-carbon bond is weaker than the hydrogen-deuterium bond. Usually you can express the difference between the deuterium rate and the hydrogen-carbon bond dissociation rate using the difference in both rate. You use a ratio. You use a KH represent carbon-hydrogen bond breaking. Kd representing the kinetics of a carbon deuterium bond cleavage. So this is also called kinetic isotope effect. Because you involved in deuterium, people also call it deuterium isotope effect. So normally the carbon-hydrogen bond or carbon deuterium bond, the breaking step is rate determining one. That step, rate determining, and then your Kh over Kd usually in the range of 3 to 8, depends on the different number of carbons. So for example, this reaction you can remove DBr, so produce this deuterium-based compounds. So one of the deuterium will be replaced. So this is an isotopic bond instead of a this hydrogen. Theoretically, this hydrogen can be removed because the deuterium bond supposedly, so you produce this the isotopic effect products. So that's what we just discussed. So you do also need a strong base, sodium alkoxide, in the alcohol solution. So this reaction turns out the ratio between KH and KD is approximately 6.7 the value. The reaction is also related to elimination E2. So what's the difference between E2 and E1? In contrast of E1 and E2, they look very similar to each other, the reaction, the chemical reaction. They look essentially identical. But in your E2 reaction, you only have 2 steps. In your E1 reaction, you have actually 3 steps. Let's see the E1 dehydrogenation. What's going to happen? First of all, in your dehydrogenation, because you don't have your protons, so you're not going to start forming the protonation. You are going to form an ion, positively charged cation. First step will be your ionization, meaning your carbon highlights that bond. For example, bromide. Carbon bromide bond will be break up. This dissociation, this bond cleavage, is heterolytic. Two electrons between carbon and bromine. These 2 electrons all move towards the bromine to form a bromide, and this carbon form a carbocation. This is also your tertiary carbocation. The first step is your slow ionization step of your alkyl halide. You simply remove the bromide, break up hydrogen bromide bond. Because you form a carbocation, so therefore this E1 reaction barely occurs in your primary alkyl halides. This step again is your slow step. So it's also a unimolecular reaction. So you call it E1. And then there are other types of reaction. You have your alcohol in your solution. So the second step you call the deprotonation. Deprotonation meaning from this carbocation. So the carbocation with a positively charged carbon. This carbon, due to the lack of octet rule, due to the less of electron, this carbon is not stable. Therefore, the beta carbon and your hydrogen, they are going to subject the bond cleavage. The reason is your oxygen in your alcohol have 2 electron pairs attracted to the hydrogen, and then this hydrogen carbon bond will be break down heterolytically. So you are going to form a bond. So due to this carbon gains 1 more electron, neutralize it. You form this butane. So 2-methylbutane, and then you form, this is called ethoxonium. This ethoxonium is not stable, like we mentioned before. It's not stable. If this is not stable, what's going to happen? This is going to subject to some reactions. So there is one more. So you have one hydrogen. How about other hydrogens? So you have the other different types of hydrogens. So you have, imagine you have this, we're talking about this hydrogen, right? So you can discussing about this hydrogen, this beta hydrogen. So the alcohol is going to remove your secondary hydrogen. First one, we're talking about the primary hydrogen. You form a less substituted compounds. And then similarly, the secondary hydrogen can be also attracted by your alcohol to form an isoxonium and your ethene. This ethene, because it's from the secondary carbon, you have more substituents. So this molecule again is more stable. And then this is called the E1 reaction for your dehydrohalogenation. So E1, generally speaking, is occurring for the tertiary alcohol halides. And then your base, you can use a little bit weaker base, but normally we use alkoxide. So this alkoxide is not charged. So this reaction is merely depends on the alcohol halides. So again, the reaction rate will be highly depends on the primary, secondary, tertiary. Tertiary halides will have the very high reaction rate. Followed by, I showed several different eliminations to form the cyclo compounds, such as these different cyclo compounds. In this case, you have 12 carbon rings that trans will be more stable. So this is your take-home message. Followed by, I also gave you some ideas about rearrangement of either methyl group or hydride, such as I have this 3,3-dimethyl 2-butanol. So this reaction can produce 3 different types of products. So what's the reason? What happened? Actually, you do subject to something called rearrangement. Rearrangement of what? Rearrangement can be the hydrogen called hydride can be rearranged. So can be methyl rearranged. So imagine this molecule. Let me go back to this. This is your 2-butanol. So 3,3-methyl. So this carbon is a secondary carbon. This is tertiary carbon. In this reaction, when you have your elimination reaction, you are producing a secondary carbocation. This secondary carbocation is going to be subjecting to a movement, to a rearrangement. That rearrangement is called a methyl shift. The methyl is going to migrating to this positively charged carbon through a 3-numbered ring, and then you form a tertiary carbocation. This is more stable. That's why you produce 3 different isomers. And also you can subject to something we call the proton, or this hydride shift. That hydride shift also resulted in the 3-numbered rings. This is what I'm saying about these 3-numbered rings. And then you further form a tertiary hydrates. The tertiary hydrates is 3-numbered center, 3-centered transition state. So that one is also related to the energy increase. That's even though the 3-centered transition state is very unstable, involved in sp3 to sp2 and then sp2 to sp3 hybridization. Hydride also can be shifted. So hydride shifting is occurred as let me moving down to this second step. So your hydride also shifted based on the 3-center transition state. So you also form a tertiary or secondary. So as long as you can form a more stable carbocation, that related product will be your preferred one. So up to this point, we essentially finished all the chapter 5 about alkene. In this alkene, we need to know several key points. So what's the alkene? What's the definition of alkene? How you are going to name the different alkene? These different nomenclatures. And then what are the physical properties? How you are going to prepare the different alkene? And what are the mechanisms for this dehydration, dehydrogenation, dehydrohalogenation, dehalogenation. Dehalogenation, we didn't discuss it in this chapter. In the future study, we are going to show you more. When we're learning about alkene addition reaction, you're adding halogens into alkene, you are going to produce vinyl dihalides. In that case, we are going to show you more dehalogenation reaction. At this point, I'm going to conclude your chapter 5 about the structure of alkene and its preparation through elimination reaction. That's all for today. Thank you so much for listening. Stay safe and stay